Welcome to Physics 151 Online. I'd like to give you an overview of where we're going this semester and then give you a brief introduction to the major topics from chapters 1 and 2. You can see that our first 2 weeks will deal with kinematics, which is the study of motion. Then we'll move into a little bit longer section on Newtonian mechanics, where we will introduce the connections between forces as the agents on objects that cause them to have a certain kind of motion. We will then go into the classic conservation laws of physics, which are the laws of conservation of energy, momentum, and finally angular momentum, and we'll finish the semester dealing with an introduction to thermal physics, including the laws of thermodynamics. So here's the outline for the first section of our course, which deals primarily with some introductory information about vectors and then one-dimensional motion or one-dimensional kinematics. We'll start with definition and properties of vectors. So a vector is a mathematical representation of some kind of physical quantity, and it's got two chief properties, magnitude and direction. Some physical properties aren't vectors, and they have perhaps magnitude but no direction. That kind of a physical quantity is called a scalar, and some examples include, for a scalar, mass, temperature, and volume. They have magnitudes, but they don't have directions associated with them. By contrast, quantities like velocity, acceleration, force, and momentum have, of course, a magnitude, a size, but they also have a direction that's implicit in their very definition. Graphically, we can depict a vector using an arrow, and then we usually give some kind of a symbolic representation. Here you can see that that is the letter A with an arrow on top of it. The vector's direction is clear from the sketch, and the length of the arrow is proportional to the vector magnitude. Now, some vectors are indeed objects that have the dimensions of a length, for example, a displacement vector. However, you might have other kinds of vectors like a velocity vector or an acceleration vector. They don't have the units of length, but we still use the length of the arrow to be proportional to the magnitude of that vector. Analytically, we usually depict a vector on a Cartesian coordinate system. So here you see the vector A drawn so that its tail is at the origin of the Cartesian coordinate system where x and y are shown. And so this vector A can be broken down into what we call components. And so the vector A, which is inclined at an angle theta from the positive x-axis, has a portion of it that lies along the x-axis, and we call that the x component, or a sub x, and then it's got a portion that lies along the y-axis, a sub y. So we can indicate this vector not just by drawing a sketch, although a sketch can often be useful, but we can indicate it by writing an equation that makes use of something called a unit vector. I hat and j hat are unit vectors that tell us that the vector A has a portion which we denote as a sub x lying along the x direction. And so I, being this unit vector, is a vector along the x direction that has a length equal to 1. J hat is a similar kind of vector along the y direction. And so we can write down this vector uniquely by writing it as a sub x times I hat plus a sub y times j hat, which means you go a sub x amount along the x direction, and then you turn and go a sub y amount along the y direction, and that takes you from the origin along the x direction and then up along the y direction to get to the tip of the arrow. And the components a sub x and a sub y have simple trigonometric relationships with the magnitude of vector A and then either the cosine or the sine of the angle that A makes with the positive x direction. So we can use either this unit vector notation, or we can use the component notation like this, and they're complementary to one another. Now, when vector quantities, when we have more than one vector quantity involved, for example, if you start off at a starting point and you walk in one direction and then you turn and walk in another direction, we often want to know what your net resultant displacement is. And if we use vector arithmetic, then we can do that quantitatively. But we can also do it qualitatively using a graphical technique, and this is often helpful because it helps us to visualize what we mean by vector addition. So if we have two vectors A and B that are indicated here on the sketch, and we want to add them together, then the way we do it is we arrange B so that its tail is at the head of vector A. And so then the resultant takes you from the tail of the first vector to the head of the second vector, and this is called head-to-tail addition of vectors. But you can see that there's also something that we might want to do. We might want to not just add two vectors, but subtract them from one another. And we can do this by simply remembering that subtracting something is the same as adding the negative of it. So if we wanted to construct A minus B, we would take the vector B, like this, indicated by the dashed arrow, and flip it over so that it points in the opposite direction. And so that is now, this vector here is now the negative of vector B. And so if we wanted to add A plus the negative of vector B, we would get the resultant here, which we call A minus B. So that's how vector addition and subtraction work. Now, it's nice to do that graphically because it helps us to visualize what's happening, but if we wanted quantitative results, if we wanted to know the magnitude of vector A plus B, it would be a little cumbersome to use a ruler and try to measure with some precision the length of that vector. So instead, quantitatively, we can use the component notation using the unit vectors I and j and add together A and B. And the way this works, of course, vector A would be ax I hat plus ay j hat. Vector B would be bx I hat plus by j hat. And so then when we add them together, we just add the components. Notice that the x components of the two vectors add independently of their y components over here. And so the sum ax plus bx tells us the net displacement along the x direction, and then ay plus by tells us the net displacement along the y direction. Now let's get into the subject of kinematics, or motion itself. You should read the other sections in your textbook that give some of the preliminaries for our subject, but I want to move right ahead and get into the physics of this and state a few definitions. If you've had a high school physics course before, then many of these will be familiar, but I thought I would run through them quickly just as review. So for a particle that is forced or constrained to move only along one direction, we're going to call that direction the x-axis. And then for it to move along that direction, we can define its average velocity as it moves from one point to another point along that one-dimensional direction. So the change in x, which is its x-coordinate along the x-axis, divided by the change in t, gives us the average velocity. But we might want to know something more than just that. This would tell us, if we knew where the particle started and where it ended up at two different times, we could calculate this average velocity. But we might want to know instantaneously what its velocity is at one particular point in time. And so the way that's done, and here's where calculus is very handy, is we imagine that we can take that interval of time between the two locations where the object is, and we can make that interval of time very, very small. So the way we indicate this in an equation is that we take that quantity which represents the change in x over the change in time, and we want to find out what that is where the change in time between the two positions becomes very, very small. We want the limiting value as the change in time goes to 0. And we indicate that symbolically by writing dx over dt. And the d represents a change, but it's a very small change. So delta means a large change, which would be the final x minus the initial x. Here we're looking at very, very small changes in x with respect to very small changes in time. And so another way of stating this is we say that this is the derivative of the position with respect to the time. The graphical meaning of this quantity is that it's the slope of the position versus time graph. And you can see some good illustrations of this in your textbook. But now let's move on and talk about acceleration. So just as velocity tells us how rapidly an object's position changes with time, acceleration tells us how rapidly an object's velocity changes with time. And so we can define in much the same way an average acceleration for this object that's moving along the x direction by defining it as the change in velocity over the change in time. And so this, of course, if we knew the velocity at two different times, then we could write v final minus v initial divided by t final minus t initial, and that would give us the average velocity over that interval of time. But of course, we might like to know what its instantaneous acceleration is, and in much the same way that we did to calculate the instantaneous velocity, we can calculate the instantaneous acceleration by taking the limit of this average acceleration as the change in time becomes very small. And there are, of course, mathematical procedures for doing this that we will use very shortly in solving problems. And so we would read this quantity as the derivative of velocity with respect to time, and that's the definition of the instantaneous acceleration. Its graphical meaning, of course, now, it's the slope of the velocity versus time graph. And so there's very similar properties that the acceleration has compared to the velocity. Now, the general expression that we would write down if we want to study one-dimensional motion would be to start with this definition of acceleration and then rearrange it just a little bit so that what we really have is an expression that says for an object moving with acceleration a in a very small time dt, its velocity would change by an amount dv. That's what this means. And so what calculus allows us to do, integral calculus, is it allows us to add up both sides of this equation over here for a time interval, and we'll add it up for the time interval starting at time 0 and going to some final time t. So by adding up both sides of this equation, and what we're really doing is taking an integral, is we're going to find out how much the velocity changes from some initial time 0 to some final time t. And so what we do, we write this down using an integral sign, which you can think of it as a very thin, tall s, which stands for summation. Now what we do in taking this equation and then integrating both sides of it is we put a prime on the v and we put a prime on the t variable. The reason for that is that I'm using a v to indicate the final velocity and a t to indicate the final time, and I don't want to confuse those limits, those symbols that we use for the limits, with the variable itself. So anyway, the left hand side means we add up how the velocity changes starting from some initial velocity v0 to the final velocity v, and the right hand side, which is equal to it, means we add up this quantity a dt starting from an initial time 0 to a final time t. And of course, when we do that, the left hand side simply becomes the final velocity minus the initial velocity, and the right hand side is just this integral. So in general, if that acceleration has a functional form that changes with time, we would have to calculate the integral using the standard techniques of integral calculus. However, the special case that we can look at here is what happens to this equation. How does it simplify if the acceleration is a constant, if it's not changing with time? And by the way, this integral has a graphical representation too, just as a derivative is graphically the same thing as a slope. When you take the integral of a function here, this a dt quantity that's on the right-hand side, what we're actually doing when we take this integral is we're integrating or finding the area under the acceleration versus time graph from time t equals 0 to the final time t. And again, you'll be able to see some nice examples of this in your textbook. So if the acceleration is constant, then it's not changing with time. It has a single value, and we can therefore take it outside of the integral. And so this simplifies the results significantly. So we find that the change in the velocity is equal to the acceleration times this change in time integral, and that's just t minus 0, or just t. And so what this allows us to do is calculate an equation that you've probably seen before, which says that if there's an object moving at a constant acceleration a for a time t, then the final velocity and the initial velocity are related like this. And that's an important equation. We'll use it quite frequently in one-dimensional motion. We can repeat this procedure starting with the general expression for the velocity in order to find the position as a function of time. And I'll go through this quickly because it follows a very parallel process to what we just did with acceleration. So if the velocity is dx dt, then we know now that that is equal to v0 plus at from what we just found. So what we will do now is take this expression, multiply both sides by dt, and that will give us dx is equal to v0 plus at quantity times dt. And what we will now do is add up or integrate both sides of this equation from some initial time to a final time. And so the right-hand side will be this integral from t equals 0 to a final time t of v0 plus at prime, dt prime. I put the primes back in. And on the left-hand side, well, at a time t equals 0, we assume the object was at a position x0, and then at the final time t it was at position x. So the left-hand side of this is easy. That just becomes x minus x0. And the right-hand side, if the acceleration is constant, what's nice is the v0 is a constant, right? So that comes outside the integral. And so we just get v0 times t for that part of the integral. If a is a constant, then I'm not showing all the steps, but this integral of at prime dt prime gives us 1/2 at squared. And you'll remember that from your calculus studies, how to do that. So then we end up with another important equation for constant acceleration motion in one dimension, which tells us that the change in position is related to the initial velocity, the acceleration, and the time according to this equation. So combining the two results that are in the red boxes, this one for the change in x and the previous one for the change in v, give us several other useful equations. And I'll just very quickly run through these without showing the steps, but I'll explain how we derive them. So equations 1 and 2 are the ones that we've just derived using simple calculus. And what happens is we can combine these two equations in several ways to get 3 more auxiliary equations. So if we take these first two equations, solve for t in the first equation, and plug it into the second one, and do a little bit of algebra, we get an equation here that doesn't have time in it. It relates the initial and final velocity, the acceleration, and the initial and final position. So that's useful, especially if we study the motion of an object and we don't know anything about the time that's involved. But there's another way that we can combine those first two equations. We can solve for a in the first one and plug it into the second one. And if we do that, we get an equation that doesn't have acceleration in it. It relates the change in x, or the displacement, to the initial and the final velocity and the time. And you can guess probably what we're going to do in order to get our final equation. We'll take the first two equations, solve for v0 in the first equation, and plug that into the second equation. And then we'll get an equation, number 5, which does not involve v0. And this equation looks kind of similar to equation number 2, but equation number 2 has v0 in it and doesn't have v final, whereas equation 5 has v final and doesn't have v0. And you'll notice that the plus sign now has become a minus sign. So these 5 equations represent a convenient toolbox to use when we're studying one-dimensional constant acceleration motion, and you will become very familiar with these equations as you work on the homework. And one final thing I'll just say is that there's a very special case of one-dimensional motion with constant acceleration, and that's when we study the motion of objects that are moving vertically near the Earth. So we throw it up in the air, and it goes up for a while, and it comes back down again, and all during that time when it's either rising or falling freely, we can take these 5 equations and realize that the acceleration, this goes back to the time of Galileo, who first realized that the acceleration of an object in this kind of situation was a constant value, independent of the size of the object or its shape. As long as there isn't any kind of significant air resistance as it rises or falls, it has an acceleration that's equal to minus 9.8 meters per second squared. Some books use 9.80, some use 9.81, so you just follow the appropriate value in your text. But we give a symbol for that, and the symbol is g. Notice here that g itself is a positive number. It's 9.8 meters per second squared. We put in a minus sign to indicate that an object is accelerating in the downward direction. And so what happens is each of these 5 equations, all we do is replace the acceleration a with negative g to get the equation that we should now use to describe the motion of an object in free fall near the Earth's surface. So each of these equations can be rewritten in just a slightly altered form, where each time we've replaced a with negative g. So these will be the starting point for many problems that we do early in the course when we're studying one-dimensional kinematic, one-dimensional motion near the Earth's surface. I hope this has been a helpful introduction to the physics of one-dimensional motion, and I will see you in class.